So before we get to differential equations, as a recap, we have to know what a function is. So y equals f of x is a function of x. Here y is the dependent variable, and x is the independent variable. And as an example, we could have y equals x squared plus x plus 1. Here we have one dependent variable and one independent variable, which is x. And it is also a simple equation. So we could have an equation where a dependent variable depends on more than one independent variable. For example, if we consider y equals f of u comma v, then this particular function has two independent variables. And the two independent variables are u and v. So, as an example here, we could have something like y equals u squared plus v squared minus 1. So in both cases, they are just equations. So we have y equals something and y equals u squared plus v squared minus 1. They are simple equations. Only we have on the right-hand side a function. The first equation, the function is x squared plus x plus 1. In the second equation, the function is u squared plus v squared minus 1, which depends on two independent variables, u and v. Naturally, a differential equation we write it as dE is an equation with derivatives of one or more functions in one or more independent variables. So what do we mean by that? Well, if you have an equation with derivatives, then naturally that is a differential equation. Now, we could have more than one function in the equation, or we could have more than one independent variable. So let's take an example. Dy over dx equals x squared plus 4. Now that is a differential equation in one independent variable and one function y, which depends on x. We could have a case where we have dx over dt plus 2 times dy over dt equals t plus 1. Here, the independent variable is t, and the equation has two functions. That depend on t, and the two functions are x and y. So now we've got to go for the notation in using derivatives. One is the prime notation, y prime, y double prime, y triple prime, all the way up to the nth derivative. And the corresponding derivative notation is dy over dx, or any dependent variable, derivative of any dependent variable with respect to the independent variable. That would be d squared y over dx squared, d cubed y divided by dx cubed, the nth derivative, or we could use a dot notation, so y dot, y double dot, y triple dot, and n dot. The dot notation is not preferred when we have equations of a higher order, so it's best we stick to the prime notation or the Leibniz notation. So what we have here is the first derivative. That would be the second derivative. And that is the nth derivative. So a key to understanding differential equations is to identify the type of differential equation that we have. An ordinary differential equation, or ODE, is one that contains exactly one independent variable. Now keep in mind, we've already mentioned that a differential equation could have more than one function in it. So if we go back to the example that I suggested over here, I have a case where I have dx over dt, dy over dt. T is the independent variable, but there are two functions, x and y, that depend on t. Now, is that an ordinary differential equation? It is, because there is only one independent variable. So if there is only one independent variable, then we call it an ordinary differential equation. So as an example, dy over dx equals x squared minus 4 is an ODE. D squared y over dx squared equals dy over dx plus e raised x is also an ODE. In a similar manner, we could have y triple prime plus 2y prime minus 4 equals 0. That is also an ODE, because by default we assume that y depends only on one variable, and that could be anything. It could be x, it could be u, it could be t, doesn't matter, but inherently we make the assumption that y depends exactly on one variable, so there is only one independent variable. So a partial differential equation or PDE is one where there are more than one independent variable. So, in contrast to an ordinary differential equation, a partial differential equation would have more than one independent variable. So, as an example, we could have dy over dt plus dy over du equals e raised u plus t. So here we have one function, which is y, and it depends on, sorry, I have to use a different notation here. It is not dy, rather we have this notation which we call the partial derivative. And as I mentioned earlier, we could have two functions in a differential equation, and those two functions can depend on more than one independent variable. So as an example, we could have the partial of f with respect to t plus the partial of g with respect to u equals 0. So here, this is a PDE. So the functions in the equation are f and g. We have two of them, and both of them depend on t, u. In other words, there are two independent variables. So we use a subscript notation when it comes to partial differential equations. What do I mean by that? Consider the partial differential equation, partial of u we need to have two variables. So here the function or the dependent variable is u, and the independent variable, there are two of them, x and y, and this is a partial differential equation in two variables. A subscript notation here is u x x plus u y y plus u x y. In many cases, the order matters, so u sub xy may not be the same as u sub yx. So I'm putting xx here because I have partial u squared divided by the partial x squared. Now we move on to the order and degree of a differential equation. So the order of an ODE is the highest order derivative in the equation. So as an example, we could have dy over dx plus 4x squared equals 0, and that's a first order derivative. So the order here is 1. As a second example, we could have that equation. So that simply means a fourth order derivative. So the order here is 4. Just like polynomial functions where we have a degree, which is the highest power of the independent variable in an equation or in a function, a polynomial function, we could define the degree of a differential equation. So the degree of an ODE is simply the power of the highest order derivative in the differential equation. So as an example, if I have y prime squared plus y double prime minus 2x equals 0, then I have a first order derivative, which is dy over dx, a second order derivative, d squared y over dx squared, and we have an order of 2 because the highest order is 2. But the power of the highest order, y double prime, is actually 1, so the degree here is 1. So there are different ways to represent a differential equation. The first one is what we call a differential form. And a differential form is used for a first order differential equation. So some function m of x comma y times dx plus n of x comma y times dy equals 0 is the differential form. Mind you that the ODE has to be of first order. As an example, let's say we have the equation y minus 1 dx plus 2 dy equals 0. Here, m of x comma y is equal to y minus 1, and n of x comma y is simply 2. Now, this is just the differential form of the first order ODE. In other words, I could rewrite this equation in this manner. Y minus 1 times dy is equal to negative 2 times, is equal to negative 2 times dy. And I'm going to solve for dy over dx, so I'm going to divide by dx on both sides, which would give me 2 times dy over dx. And I'll divide by negative 2 on both sides, which would give me dy over dx equals y minus 1 divided by negative 2. So this differential equation right here is the same as that equation, only that the first equation is in the differential form and the second one is simply a differential equation. So if we have a first order differential equation, then we can write it in a differential form. Then we have something called the normal form of a DE. So it is a form where the highest order it's one where the highest order of the derivative is expressed in terms of its lower orders and constants. So what do I mean by that? So suppose we have the differential equation y triple prime plus xy double prime plus 4 equals 0. That, by default, is in the normal form. If I rewrite it, I could rewrite it as y triple prime is equal to negative xy double prime plus 4. So the highest order is y triple prime, and I'm writing that in terms of the lower orders, which is y double prime and the constant term 4. Another example for a differential equation in normal form could be one of this sort. So what we have is I have expressed the highest order in terms of its lower orders and other functions, which is 4x and e raised x of the independent variable. So the goal of differential equations, just like, an equation in algebra, is to find a solution. So our objective is to find the solution to a DE. In particular, solution to the function or functions in the differential equation. For example, we have some function dy over dx is equal to x cubed over 2. Our goal is to find So we just have to find a solution to y that satisfies the above differential equation. Now, one thing that we have to be very careful when it comes to differential equations is the interval of existence. So So interval of existence, or a solution interval, is an interval where the solution to the differential equation is actually valid. So the domain of a function is a set of all x values for a function. So just because you get a function as an answer doesn't imply that it is going to work for all values in the domain of the function. So a differential equation would always come with an interval of existence. As an example, consider dy over dx is equal to xy squared. So we would like to know if y equals minus 2 over x squared, a solution to the equation. So this is a first order dE. So dy over dx is equal to xy squared, which would mean dy over y squared is x times dx. Now, the simplest way to find a solution here is to find by integrating. We will cover this later on. So I'm going to integrate on both sides. So integral dy over y squared is equal to integral x times dx. So dy over y squared would give me y raised negative 2 dy equals x dx. So we will have y raised negative 1 over negative 1 equals x squared over 2. Y raised negative 1 would equal to negative x squared over 2. I'm ignoring the constant of integration. Y raised negative 1 would simply mean 1 over y. So which tells us y is equal to negative 2 over x squared. Now I pretty much have shown you the way to find the solution to this particular equation. But is there a different way to verify this? So we have y equals minus 2 over x squared, and I would want to plug that in the given dE, which is dy over dx is equal to xy squared. So what is dy over dx based on the solution? So d over dx of negative 2 over x squared, I'm plugging in the value of y, and when I take this derivative, it must match up to xy squared. So which in this case is simply x times negative 2 over x squared squared, which is x times 4 over x raised 4, so 4 over x cubed. So I'm plugging in y equals negative 2 over x squared in dy over dx. Let's see if we get 4 over x cubed. So this would be the derivative of d over dx, negative 2, x raised negative 2, which is negative 2. The power comes to the front, and we decrease the exponent. This is just power rule of derivatives. So we end up having 4 times x raised negative 3. So that would simply be 4 over x cubed. So dy over dx matches with the right-hand side, which is xy squared. And based on this verification procedure, we have established that y equals negative 2 over x squared is a solution to a differential equation. So if we have a solution to a differential equation, when we plug this solution, which is a function, back in the differential equation, the left-hand side must match up to the right-hand side. This is very similar to what we do in algebra. What is the existence interval for this particular function or differential equation? Even though we have y equals negative 2 over x squared, note when x is equal to 0, y doesn't exist. So the solution for this particular differential equation is negative infinity all the way up to 0, union 0 to infinity. We're not including 0 because there is a discontinuity. We get divide by 0 when x is equal to 0. We should also keep in mind that there are other solution intervals that are feasible. I could have 1 to 10 as a solution interval. I could have 2 to 100 as a solution interval, and so forth. Any interval, as long as I don't include 0, would be a valid solution interval depending on the problem. So anytime we have a solution to a differential equation, we have to make sure that it satisfies the equation like it did here for a set of values. In this particular problem, the differential equation exists, and it exists for all values except 0. And when we have a solution to a differential equation, we actually have two types. One is an explicit solution, and the second is an implicit solution. An explicit solution is one where the solution depends only on the independent variables and constants. So, for example, in the previous problem, dy over dx equals xy squared. That was our differential equation. The solution that we verified was y equals negative 2 over x squared. As you can see, that value y, the solution y, depends only on a constant, which is 2, and the independent variable x. So that solution is explicit. So the solution to the differential equation is dependent only on constants and the independent variables. Naturally, an implicit solution would just be the opposite of an explicit solution. So suppose we have some function g of x comma y equals 0, and g of x comma y is an implicit solution. Of course, it's going to have some open interval or interval that would be the solution interval. So we would call it an implicit solution if there exists some function we'll call it f that satisfies the relation that g of x comma y equals 0 and the differential equation in and of itself. So let's say we have x squared as an example. Consider x squared plus y squared equals 16. Now I could rewrite this as x squared plus y squared minus 16 equals 0. So I have a relation here, and that relation is g of x comma y. And we want to know if that is an implicit solution for the differential equation. For the dE, dy over dx equals negative x over y. And the existence interval here, x squared plus y squared equals 16, is a circle. So the solution has to happen within the radius of the circle. So the existence interval would be negative 4 to 4. So I am going to take the derivative on both sides. So you have 2x plus 2y times dy over dx equals 0. Implicit differentiation. This is from calculus. Divide by 2 on both sides, we would have x plus y times dy over dx is equal to 0, which would imply y times dy over dx is equal to negative x, which would mean dy over dx is equal to negative x over y, which clearly satisfies the differential equation. And the simpler way to look at it is an implicit solution is a solution where where we don't have the solution y independent, depending only on the constants and the independent variable. So here we have a function of y, which is y squared, equal to 16 minus x squared. If we rewrite the solution, we have y squared is equal to 16 minus x squared. So in an easier sense, it's not just y is equal to 16 minus x squared, rather it is a function of y that is equal to 16 minus x squared. And the way we could satisfy the relation is via implicit differentiation, and hence the reason we call the solution an implicit solution. Another example for an implicit solution, to make a point, suppose we have y squared plus 2xy minus 1 equals 0. So in that case, we have y squared equals 1 minus 2xy. So in a way that y squared is dependent on y itself. So that is an implicit way of looking at it. So that solution is an implicit solution. And oftentimes you could take an implicit solution and rewrite it in a certain way, or rewrite it so that the implicit solution ends up becoming an explicit solution under certain conditions. It is feasible. So just like we have system of linear equations or system of equations, we could have a system of differential equations. So suppose we have two functions that depend on the independent variable u. And as an example, I'll just demonstrate this with an example. And dx over du is equal to x plus u plus 2y, and dy over du is equal to xy squared plus 4. So we actually have two differential equations. So this is an ODE for x, and this is an ODE for y. And we would like to find a solution that would satisfy both of these equations, and that particular solution would be the solution to the system of the two equations. So this is what we call a system of differential equations. So the goal here is to find solutions for x and y, i.e. some function of u, so that it satisfies both d's.